This is Lab 3, so this is a continuation of error detection and correction. Today we'll be talking about calculating checksums. When we learned about parity, we used a single bit to check a number of bytes. Checksums work by using a single byte to check the number of bytes that are a part of a block. They help us find errors in larger units of data. So when we first download the code to Visual Studios, we get an error message on the main part of the code. That's because we need to include the checksum.h file, which is where we defined our enum data type and function prototypes, which can be found on the Lab3 PowerPoint. So we need to go to the header file. The unsigned integer checksum allows the main method to access the function that is written in checksum.c. So when looking at our checksum.c file, we started by including the standard.io so we can print our error message to the user. And we include our checksum.h file so that we have access to our enum. So in this function, we will be using switch cases. In switch cases, we have different scenarios. So in this function, there will be 3 cases. In this checksum function, our 3 cases is checking if it's 16 bits, checking if it's 8 bits, or if it's neither. So if it's neither, that is essentially the default case, which is where we can print our error message to the user. So what this is giving us is a pointer that hasn't been casted to any specific data type yet. If you want to do a 16-bit checksum, we would need to cast this pointer to a short because the data type for 16 bits in C is a short, while the data type for 8 bits is char. These are pointers for casting. So what this line is doing is reorganizing the groups. We want to organize groups so that they are organized into 16-bit groups. So what itype is determining what the data type is. iBuff length is how many elements there are, and buff is the memory location. So when we know these 3 things, we can check the sum. So before checking the sum, we need to get the sum first. And to do this, we can use a loop and a counter to go through each element. So we've initialized the sum and checksum as 0 because we have to start at 0 and then count our way up. So we know sum equals sum plus whatever is in the memory storage or wherever the pointer is. So in this case, we know it would be sum plus star new buff 16. After we've added to the sum, we want to move on to the next. We want to move on and do the same to the next 16 bits. We know that plus plus indicates that we are incrementing something, and because new buff 16 was casted to a short, we know that saying new buff 16 plus plus means we are incrementing by 16 bits over. So after this loop and getting the sum, then we can do the checksum, which is where we can implement the equation we got from the PowerPoint presentation. So checksum equals sum mod 0x10000, and the reason why we mod it by that is this is a hex number and is the maximum number that 16 bits represents. So once we do that equation and calculate it, we can return the checksum to the main function. So the same thing is done with check 8-bit, but instead of casting it to a short, we are casting it to a char. But the same concept that we did for check 16-bit is done for check 8-bit. The only difference is the data type and that we aren't moving along 16 bits, but 8 bits. And when we calculate the checksum, the maximum number we can represent 8 bits is 0x100, which is what you would mod the sum by. Then we can return this checksum to the main function in this case. And then the default lets the user know there's an error. It's where we can simply print out there's an error and return that. So the size I chose here is 32 bits. And so now we can run our program. So our checksum of 8-bit buffer is 66. Then in the main code, we asked it to alter the buffer by randomly choosing a byte and then doing the same for a bit in that chosen byte and then flipped one bit in the buffer, then computed the checksum value. So the function checksum works.